Okay, welcome to physics. As usual, we're going to take a quiz before we talk about last night's homework. There is one thing that's going to be a little different, not for those of you in the B-Day class, but for those of you in the A-Day class. I will not be able to host a live session on Tuesday. I've got another appointment that I can't get out of. So I am going to post this recording on Canvas, and just so for the A-Day people, you're going to be watching this recorded rather than those of you in the B-Day class. For you guys, it's live. Okay, so regardless of whether you're in the A-Day or the B-Day class, what I'd like you to do right now is to log on to Canvas and go to the quiz, which, okay. So the quiz is now open and it's named Quiz 3A. And as usual, you've got 5 minutes to complete it. As usual, if you don't think that's enough time, don't sweat it too much. You know that you can retake quizzes, but give it your best shot. So I'll let you guys go ahead and get started on that. And I will pause the recording. So there's no sense in running the recording right now. So those of you in the A-Day classes, take the quiz now, even though you're watching a recorded version rather than a live version. I still would like you to take the quiz now. All right, so I'll see you guys in about 5 minutes. All right, I just restarted the recording. I see one, no, okay, now everybody's now done. All right, and I see that some people did pretty well. Many of you did not. So if you're one of the people that didn't do well, remember that you can retake every quiz. You just need to wait a little while because I need time to go through and look at everybody's results so I can make notes of who is getting what, and who's having trouble on which things. And so after I've had a chance to go through and look at everybody's results, then that includes both the B-Day as well as the A-Day classes. Then I'll unlock the quiz and let you go in and have a second try at it. But remember, you have to send me an email telling me you've redone it. Otherwise, it will not get updated in Aspire. So what I'm seeing right now, there are enough of you who did not get perfect scores that it has me a little worried that some of you aren't learning what you're supposed to be learning from the homework. So we're going to go over the homework right now. And hopefully we can clear up some of the questions that you clearly, at least some of you clearly didn't understand. Others of you did quite well. Okay, so let's see. All right, no comments there. Okay, so let me, okay, here are the answers to last night's homework that you haven't looked up. Now, the vast majority of last night's homework problems were odd numbered ones, and so the answers were in the back of the book. So you should have already had a chance to look them up and see if you did them right. There were only 2 problems where the answers weren't in the back of the book. So here are the answers to those. So if you're one of the B-Day students who's participating in this class live, you can go ahead and ask questions now. If you're one of the A-Day students, sorry, you're just out of luck. Okay, so B-Day class, do you have any things you want to go over? Not seeing anything, not hearing anything. The chat window just disappeared. It does that sometimes. I hate it when it does that. So I have to stop sharing my screen. And now I can see the chat box again. And no, I'm not seeing anything. Oh, there we go. Okay. So one student wants to go over 28. Okay, can do. All right. So let's see what 28's asking. Okay, so we've got a bike rider going with a constant acceleration to reach that speed over time. Okay, so let me turn on the annotation here. All right. So they say that the constant acceleration is, well, they actually they don't give a number for it. Okay, so we don't know what the acceleration is, but we do know it's constant. And the fact that it's constant means that those equations that I gave you do apply. Remember, those equations that I gave you, the ones that I like to call the Dr. Seuss equations, they only apply if the acceleration is constant. But that will be the case for all of the problems that we do in the high school physics class. Now, next year, hopefully many, if not most of you, will take the University of Utah physics class. Now that one, the acceleration is not always constant, but for us it is. Okay, so we reach a velocity of 7.5. So it sounds to me like that's V final is 7.5 meters per second. Okay, and they don't tell us what the V initial is. So let's see if we can figure out what that is. Well, I guess we're going to have to make an assumption here. So that might be the reason why you had trouble with this, is because they don't tell you what the initial velocity is. So I'm going to make an assumption here that it's 0, because otherwise I think the problem's unsolvable. All right, and they do tell us what the bike's displacement is. So remember that delta x is displacement. That's final minus initial. And they say that the displacement there is 19 meters. All right. So, oh, wait a minute. I should read the whole problem before I start talking about it. They're asking what the initial velocity is. Okay, sorry. Okay, so they're not asking what the acceleration is. They're asking what the initial velocity is. So apparently I was wrong in assuming that the initial velocity was 0. Right? Okay, so we don't know what the acceleration is. We're looking for initial velocity. So what I like to do is I like to put a box around the thing that we're looking for. Okay, so now we're going to have to go look at the equations, the ones that I like to call the Dr. Seuss equations, but the official name is the equations of motion. Okay, and we need to find an equation that has a v final in it and does not have an acceleration in it. All right, so let's go look at those equations there. Okay, there they are. Okay, so let's look at these and see which equation has a v final in it, but does not have an acceleration in it. All right, so the mother of all motion equations, nope, that's not going to work because it's got an acceleration. Second one down is not going to work. Third one down is not going to work. We're running out of options. Oh, wait a minute. The very last equation. Okay, it's got a v final in it, which is good. And there's V initial, which is the one that we were looking for. So if it didn't have a V initial in it, it wouldn't do us any good. Okay, but it does. And X final and X initial. Okay, so I think we're in good shape. That's the one we want to use. Okay, so make note of that. So X final is X initial plus 1/2 V initial plus V final times T. Okay, so let's go back up to the previous page. All right, so our equation then is, whoops, wrong way. I have to turn on annotation again. Okay, so actually now I forgot what it was. I should have written it down here. Okay, so let me write it down. So X final equals X initial plus 1/2 V initial plus V final times T. Okay, now that I've got it written down, let's go back here. Turn on annotation again. Oh, and by the way, how about let's get rid of these guys here. Okay. All right, so if our equation was X final equals X initial plus 1/2 V initial plus V final times T. Okay, so that's supposed to be a T. That looks like a plus sign, but it's a T. All right. So V initial is what we're looking for. Now notice I called it V with a 0 over here, whereas over here I called it V with an I. So get used to that. I'm going to be using those interchangeably. They both mean the same thing. All right. So we just need to do a little bit of algebra here. I trust that you guys are good at algebra. So first thing let's do is let's get rid of that X initial. Okay, so we're going to have X final minus X initial equals 1/2 V initial plus V final times T. All right. And X final minus X initial, that's just delta X. So we know that. Okay, so we got to get rid of the 2 and we got to get rid of the T. So, okay, if I want to get rid of the 2, how about I multiply both sides by 2. So the 2 cancels the 1/2, but whatever I do the right side, I have to do the same thing left side. Let's divide both sides by T. That gets rid of that, but whatever I do the right side, I have to do the same thing left side. All right, and so now we're left with V initial plus V final. So let's get rid of the V final. So let's subtract a V final from each side. Okay, so that goes away. So now we're left with V initial equals all of this. All right, so let's just plug that into our calculator. So V final was 7.5. So I'm going to do negative 7.5 plus 2 times delta X, which was 19, and divide that by the time, which was, oh, I didn't write that down. The time was 4.5 seconds. I should have written that down. So T equals 4.5. Okay, so I'm going to divide that by 4.5. Okay, so I get, wait a minute. What am I doing wrong here? Am I looking at the wrong problem? I'm looking at the wrong problem. Oh, I'm so sorry, guys. Okay. You are probably, I'm sure you guys are all sitting there wondering, what the heck is Mr. Hendricks doing? I was looking at problem number 29, and you were asking about problem number 28. Oh, I am so sorry. Okay. Well, we just did problem number 29. But that wasn't the one that you wanted, Julie. I'm very sorry. Okay, wrong problem. Okay, let's go back and I would say that that's a wig point, but it wasn't really a physics mistake. It was just me reading the problem wrong. How come nobody spoke up and said something? Guys, when I do silly stuff like that, you need to speak up. It's your guys' job to keep me up. So let me make sure that I understood the problem again. So I can't see the chat box. It was 28. It was 28 that she was asking about. Okay, so let's go back, and this time let's do 28, not 29. I really sincerely apologize for that. Okay, so 28. So we've got the car starts off at 15. So V initial equals 15 meters per second. V final equals 25 meters per second. It travels a distance of 120 meters, 25 meters. That's supposed to be a 5. Okay, and we want to know how much time it takes. All right. Okay, so so again, we have a problem where we don't know what the acceleration is. But if we're lucky, maybe we don't need to know. Okay, and so let's find an equation that has a t in it but doesn't have an a in it. Well, hey, I'm thinking it's the same problem that or the same equation that we had before. So x final equals x initial plus 1/2 v initial plus v final times t. All right, so this time we're looking for t. So let's subtract x initial from each side. So x final minus x initial equals 1/2 v initial plus v final times t, right? So now let's multiply both sides by 2. And let's divide both sides by v initial plus v final. Okay, and so this then equals t. All right, so let's try it again, this time using the numbers for the correct problem. So we had 2 times, so x final minus x initial, that's just delta x. So 2 times 125. And we're going to divide that by v initial plus v final. Make sure you put that in parentheses. If you got a wrong number, it could be because you left out the parentheses. So v initial is 15 plus v final is 25, and that's in parentheses. If you leave that out, it'll screw everything up. Okay, so I get 6.25. And if you compare that with the answer there, you can see what the author in the book has done. He's realized that 3 sig figs is too many. We're not allowed that many. So we had to round it up to 6.3. Okay. So I apologize for the little detour I took there by doing problem number 29 instead of number 28. Does that answer your question? Okay, good. All right. Any other questions before we move on? Not seeing anything, not hearing anything. Okay, so let's go ahead and move on to the new material. Okay, so today we are going to finish chapter 3, and then we will be ready for our next test. Okay. So I am going to be giving out a practice test, which is a review sheet. It's actually on Canvas right now. I just put it on there this morning. If you want, you can go ahead and download it and take a look at it. I would recommend that you do the homework problems from 3B first. And then after doing those, then I would recommend you look at the practice test. The homework problems for 3B, those are a required assignment, and you will, so 3B is a required assignment, and you need to do those in order to get the 10 points that will go into Aspire. The practice test is not a required assignment. It's just there for your benefit. If you choose not to do it, if you're so confident that you don't think you need a review, you know, hey, that's good for you. But I'm thinking most of you will want that. But 3B is the required one. Okay, so let's talk about what you need to know in order to do 3B. Right, so first off, when you read 3B, when you read the chapter prior to doing the homework, because I know you always read the chapter prior to doing the homework, right? You're going to see that we talk a lot about free fall. And so free fall, whoops, okay, I keep forgetting to turn on annotation before I touch my screen there. All right, so let's suppose you're up on top of a big tall building. And so here's you, and you're holding a rock in your hand. Okay, so if you let go of the rock, obviously it's going to fall. It starts off moving slowly, and then it gets faster and faster and faster. So as the thing is falling, that's free fall. And everybody that I've taught over the years has no trouble understanding that. But sometimes people get confused where if instead of dropping the ball, what if we throw the ball? So let's say that we throw the ball upward. So it's got some initial velocity in the upward direction. Okay, so what's going to happen? Well, the ball is going to go upward. It's going to slow down, and then it's going to eventually reach the highest point. And so the velocity will be 0 at that point. And then it'll start falling. And then the distance gets further apart. So one common misconception that students often have is they think that free fall only applies during the time when the thing is falling down. And so if I ask students, is the object in free fall while it's moving upwards? A lot of students respond, no, it's not, because it's moving upwards. They say, well, you know, I mean, I can understand what they're thinking there. I mean, it makes logical sense that something would only be in free fall if it's actually falling rather than when it's going up. But that's not the way that physicists define it. Okay. So if I take this pen and I throw it upwards, as soon as it leaves my hand, it is in free fall, even during the time when it's still moving up. Okay, it's slowing down, but it's still moving up. That it's still in free fall, even during the time that it's moving up. Okay, that's something very important that everybody needs to understand. So any object that is acted on only by gravity is in free fall. Okay, so make sure that you understand that. So if we do a bunch of experiments where we take something, like for instance, let's say I take the pen and I drop the pen, and if I had some sort of tools that would allow me to measure the acceleration, anybody know what I would get? What number would I get? I'm sure that many of you do. So type it into the chat box here. If you're in the B-Day class, if you're in the A-Day class, you're just out of luck. Okay, so those of you in the B-Day class, I'm sure some of you know, what number will I get? Aha, so AJ is saying that it's about 9.8. Now AJ actually gave it 3 sig figs. He said 9.81. We're going to find out later that that third sig fig, well, it depends on where on the earth you are. Okay, if you're at the equator, you're going to measure a slightly different number than somebody who's here in Utah, and slightly different again from somebody who's up at the North Pole. If you go at 2 sig figs, then everybody's going to get the same number, because when you round it off to 2 sig figs, you know, everybody, you know, the difference is so slight that it all rounds to the same number. But if you want to record it with 3 sig figs, you're going to find out that it's actually different. Okay, so let's just go at 2 sig figs for now. I don't want to complicate things. So if you're measuring it in meters per second, then AJ and Max are both right. If you round it off to 2 sig figs, don't go 3. Okay, so in meters per second, it turns out to be 9.8 meters per second per second. Okay, now if you were to measure it in feet per second, then it would be 32. But in this class, we're going to try to avoid using feet as much as possible. We're going to try and stick with standard physics units. Okay, so with that being in mind. So if we are, whoops, I keep forgetting to turn on annotation. Okay, so if we are standing here on this big tall building, we drop the rock falls. So the acceleration will always be 9.8 meters per second downward. Notice that I had to put a direction on that, because acceleration is a vector just like velocity and just like displacement. In order to completely answer the question of what the acceleration is, not only do I have to tell you what the magnitude is, remember this is the magnitude, but I also have to tell you what the direction is. Okay. And that applies even when I'm throwing the ball upward. Okay, so when I throw the ball upward, let's keep things really simple right here. Let's just go with only 1 sig fig, okay? So if I only go with 1 sig fig, do you guys agree that 9.8 rounds up to 10? Okay, so for the next few minutes here, I'm going to just keep things down to 1 sig fig just to keep things really simple. So let's suppose that when I throw the ball, my initial velocity is 25 meters per second. Okay, so 1 second later, it will have decelerated. It will, because the acceleration is negative and the velocity is going up, right? So I'm going to have deceleration of 10 meters per second per second. So are you guys all agreed that the velocity 1 second after it leaves my hand will now be 10 meters per second less than it was initially? So when it gets, let me switch to a different color here. Okay, so when it gets to this point right here, where t equals 1 second, the velocity now is only 15 meters per second. 1 second later, notice it hasn't traveled as far now. The velocity now is 5 meters per second, and these are both upwards. What will the velocity be 1 second after that? Okay, so I want somebody to type in the chat box. So at t equals 0 here, in fact, tell you what, let's make a table. Let me clear some space here. Let's make a table here of what the velocity is going to look like. So here's time, here's the velocity. So at t equals 0, the velocity is 25 meters per second upward. At t equals 1, it's 15 meters per second upward. At t equals 2, it's 5 meters per second upward. What will the velocity look like at t equals 3 seconds? Can somebody, let me just make my numbers a little bit more legible here. I need somebody to type something in the chat box, guys. What will the velocity look like at t equals 3? Notice how every second that goes by, it's getting 10 meters per second less than it was before. So, okay, thank you, Fatima. Yes, 5 minus 10 is -5. So that means it's going to be 5 meters per second going downward. At t equals 4, it's going to be 15 meters per second going downward. At t equals 5, it's going to be 25 meters per second downward. And then at t equals 6 is going to be 35 meters per second downward, and so forth and so on. Okay. Now the real number is not really 10. The real number is 9.8. So be aware that these numbers you're seeing here are approximations. Notice the velocity 5 seconds after it left my hand. That's when the thing has gone up, turned around, and come back. So what we've just figured out is that when it reaches my hand again, if instead of letting it keep on falling, if I were to catch it, it will be traveling at the same speed that it was when it left my hand. It'll just be going downward rather than upward. And what we see here is that the time required to make this whole trip here is 5 seconds. So the time going up is 5 seconds, time coming down is 5 seconds. Okay, so now during all of this time here, the ball was in free fall, even during the time that it was going up. Okay, so I hope everybody's good with that. Any questions before I move on? Okay, so hopefully we all know what free fall is. Okay, so basically all of your homework tonight is going to be involving things that are in free fall. So there really isn't any new material that we learned tonight. All we're going to do is we're going to take the equations that we learned last time, and we're going to just use those equations to solve a whole bunch of problems with objects that are in free fall. And that is all of tonight's homework, okay, is just that. So it'll be good practice doing the stuff that you should have learned last night, but apparently what I'm seeing there on Canvas is telling me that some of you didn't. All right, so let's say that we throw a ball vertically upward and we want to know how high it's going to go. And this time we're not going to use 1 sig fig. This time we're going to use 2 sig figs. All right, so here's the ground. And let's say that when the ball leaves the ground, it has an initial velocity. Oh, let's just pick a number. Let's say our initial velocity here is 27 meters per second. And that's our initial velocity. I want to know how high the ball is going to go, because I know what's going to happen is it's going to go up to the top there and it's going to stop. Okay. So one thing that I could do is I could make up a table of time and velocity. So I know at t equals 0 is 27. At t equal 1, it's going to be 27 minus 9.8. And I could keep on going there. At t equals 2, it's 27 minus 2 times 9.8, and so forth and so on. And I could try and figure it out from the table, but it's not going to work out very easily that way. It's not going to work out to be a nice clean number. Let's use the equations. Let's use the equations of motion to figure out how high this thing goes. Okay, so here is the technique that I recommend that everybody use for all of these problems here. Let's make a list of all of the variables that we see in the equations of motion, what I like to call the Dr. Seuss equations. So I'm going to call these the Dr. Seuss variables. So let's say we've got x initial, x final, v initial, v final, a, and t. And let's fill in what values do we know and what values are we looking for. Okay. All right, so notice that the origin has not been specified. We are free to choose that origin anywhere we want. So I recommend we put the origin at wherever the ball was when the ball started. When we started the clock going, wherever the ball was, that's going to be our origin. And so x is defined always to be how far away from the origin is the object. So x naught, or initial x, that's defined to be how far away from the origin is the ball when we started the clock. Well, if we put the origin at the place where the ball was when we started the clock, by definition, then x initial is going to be 0. X final, we don't know. And in fact, that's what we're looking for. The question here is saying, how high will it go? So what that means is x final, that's what we're trying to find out. So you'll notice I put a box around it because that's just to remind me that that's what it's looking for. V initial, well, we just got through saying that's 27 meters per second. Now, we need to, in addition to defining where the origin is, we also need to define what direction is the positive direction. Now, most people are most comfortable with having the positive direction being up. You don't have to do it that way. You could define it to be down if you like to be different, but seeing how most people like it that way. So then what I'm going to say is our initial velocity is a positive 27, and that's going to be meters per second. Okay, now, when are we going to stop the clock? Well, if we're interested in how high the ball is going to go, don't you agree that this makes the best place here to stop the clock? So because that's what we decided we wanted x final to be, right? So when the ball gets to the x final position, that's when we're going to stop the clock. All right. So I need somebody to type into the text box. What do you think v final is going to be? What do you think that the velocity is going to be when the ball reaches the highest point? Okay, so Max is saying 0. You guys agree? Okay, so even though the problem does not specifically say v final equals 0, you guys need to be smart enough to realize that when that ball reaches the highest point, okay, it's going to stop for a brief second and then it's going to start heading downward. So you need to be able to recognize that v final is 0. Okay, now what about the acceleration? Well, the problem here doesn't really say what the acceleration is, but if we assume that we're on the planet Earth, which is a safe assumption, unless the problem says otherwise, you can assume it's planet Earth. So what is the acceleration going to be for an object that's in free fall on the planet Earth? I need somebody to type it into the chat box here. Okay. So Lucas is saying 9.8. Okay, good. Now that's the magnitude of the acceleration. I agree is 9.8. But remember, acceleration is a vector. That's supposed to be a second. Okay, so 9.8 downwards. Okay, so if I define that the positive direction is upwards, when I put in my acceleration here, I better not put it in as a positive 9.8. That's going to screw everything up. I need to put it in as a negative 9.8. All right. Okay. And then the last variable in our list here is time. And nowhere in the problem did it say anything about that. So we're just going to have to say that we don't know the time. And maybe if we're lucky, we don't need to know the time. Right? So let's look at our variables here. So the thing we're looking for is x final. Now, so when we go to our poster, which by the way, I hope you guys have downloaded that file and printed that file out. Okay, so when we go to that page that has all the Dr. Seuss equations on it, whichever equation we pick had darn well better have an x final in it, because otherwise it's not going to help us out. Now it might have a delta x in it, because delta x is just the same thing as x final minus x initial, right? So it's got to have an x final or a delta x in it, otherwise it's not going to help us out. And since we don't know the time, it had better not have a t in it, because if it has a t in it, then we're going to have a problem, because we're going to have two variables in there that we don't know, because we don't know what the x final is, and if we don't know what t is, we got two unknowns, and if you got one equation and two unknowns, hopefully you guys realize that doesn't work. All right, so let's go back to our equation here. Okay, so I apologize for all the scribbles on the screen there, but take a look at that. Do you see any equations that don't have a t in it? How about this one, right? Whoops, I keep doing that. Okay, so how about the third one down? Let me just turn on annotation here and switch to a different color. Okay. How about this one right here? Does that do what we want? Does it have either an x final or a delta x in it? Yes. And does it not have a t in it? Good, because if it had a t in it, we'd be in trouble. Okay, so that's the one that we want. So now let's go back down to here. Okay, and let me get rid of this. Okay, and now I need some more room. Here, teaching online here has some serious problems. If I was working in my room, I have whiteboards all over the place, so I don't need to erase stuff. But in this case, unfortunately, I do. All right, so let's erase all this here. All right, so the equation that we figured out that we needed was v final squared equals v initial squared plus 2a delta x. All right, so delta x is what we're looking for. So let's get out our algebra skills here. I mean, you guys are going to be so good at algebra when this class is over. So if this is what I want, let's get rid of everything that's not delta x. So let's subtract v initial squared from each side. So that gives me v final squared. Let me get rid of that. Okay, minus v initial squared equals 2a delta x. All right, what I need to do next, I need to divide by 2, and hey, while I'm at it, let's divide by a at the same time. So divide that by 2a, so that goes away. So that means delta x then is equal to this. All right, so v final squared, well, that's just 0. V initial, and don't forget there's a squared there. It's hard to see. There's an initial squared. Okay, so that was 27. Okay, so I need to take negative 27 squared divided by 2, and also divided by a, which we hopefully know is negative 9.8. So the two negatives are going to cancel each other out. Okay, so when I do that, I get 37. So x final 37.19 and a bunch of other digits, okay? So that's what my calculator tells me is the answer. Is that my final answer? Is that what I write down on the sheet? Hopefully you guys realize the answer is no, because that's too many sig figs. So I got to figure out, okay, how many sig figs am I allowed? Well, if I look at all my input numbers, I see they all have 2 sig figs. So that means my answer better have 2 sig figs as well. So here's what I recommend you guys do when you take the test. Write down the number that your calculator gives you, and then an arrow, and then tell me what the rounded off number is. So x final equals 37, okay? And then circle that or square it or something, okay? And the reason that I want you to write down the number that you see on your calculator is because a lot of times people round off wrong. They look at this number, 37.19, and they round it up for whatever strange reason. I don't know what they're smoking at the time, but I know people do it all the time. So they round it up to 38 when they should have rounded down to 37. So if all I see is their final answer, and if they didn't tell me what the initial answer was, and I have to try and figure out whether or not I should give them partial credit on the test, I don't know whether they made a physics error or if they just made a round off error. Okay. But if they did tell me what the calculator said, then I can see, okay, they did the physics right, they just rounded off wrong. So in that case, I can be a lot more generous with partial credit. And by the way, I want you guys to be aware of something important. If you've talked to any of the students from previous years' classes, you'll find out they'll tell you, I will be very generous with partial credit if you show your work. And if your work shows that you understood, mostly what you were doing. Okay, if you go through and you show every step, and I can see that you knew what you were doing, but just on this one little step here, you made an algebra error, you left out a minus sign, or some silly little algebra mistake. If I were to give you a test question that's worth 5 points, even though your answer is completely wrong, I could give you 4 out of 5 points, because if you show your work and I see that you just made a silly algebra mistake, hey, I'll only take off 1 point for making a silly algebra mistake. But you gotta show your work, because if you don't show your work and I see that your answer is wrong and you didn't show your work, I'm gonna have to give you 0 out of 5, whereas otherwise I could have given you 4 out of 5. Okay, so really important, guys, show your work. Okay, all right, so okay, so hopefully we're good now at figuring out how high balls are going to go when we throw them upward. Now, what if we want to know how much time the ball is going to be in the air? All right, because you never know, you might see a problem like that on your homework and on the midterm exam. Okay, so a different problem now, but again, similar. Let's say that our initial velocity is a different number this time. Let's say our initial velocity is 43 meters per second. And so the thing goes up and reaches the highest point here, and then it's going to come back down to the ground. So I want to know how much time will the ball be in the air, okay? So there are a couple of ways we could solve this, and I'm not going to take the time to do all of the different ways. I'm just going to pick one way. And if you look in the book and you say, well, the book suggests a different way, that's okay. They're both equally valid. What I'd recommend is let's break this problem into 2 parts. Let's find out how much time does it take to go up. And we know that the time it takes to go down will be the same. So if we can just figure out how much time it takes to go up and then multiply it by 2, that will that'll give us the right answer. Okay, so how about let's use this. So if you go back to the equations of motion page, so okay, you'll see that the second equation down, the one that says v final equals v naught plus at, I'm thinking that's going to be the simplest one to do. So let's take that. So v final, okay. So v final equals v initial plus at, right? So we know what v final is, right? We know that when it reaches, it's going to be 0. So v final equals 0. So we know v final, we know v initial, we know the acceleration. The only thing we don't know is t. Bingo, that's the one we want. Okay, so let's get out our algebra skills here. So let's subtract a v initial from each side. And let me clear this away to make some room here. Okay, so that gives us v final minus v initial equals at. All right, let's divide both sides by a. And there we go. So t then equals that, right? So v final we know was 0. So v initial was 43. So minus 43 divided by acceleration. Now, is the acceleration 9.8 or is it negative 9.8? Well, if we said that v initial is 43, then that means we must have decided that the plus direction was going up, because we put v initial down as a positive 43. Okay. So that means that our acceleration due to gravity, which by the way, you're going to see that it's called g. It's such an important number that it's got its own letter. So g is going to be the acceleration due to gravity. And the magnitude of g is always 9.8. And if we chose our plus direction to be up, then that means that the g that we have to use is going to be negative 9.8. So we got 43 divided by, or negative 43 divided by negative 9.8. So the negatives cancel. So the time there works out to be 4.387, which is too many sig figs. So then I put an arrow and I say 4.4 seconds. But that's only the uptime. So I probably shouldn't have put a box around that. That is only the time that it takes to go up. Okay. So if the question is asking, what is the total time that it's in the air? So the total time that it's in the air is going to be twice that. So what I should have done is I should have taken this number you don't want to round off till you get to the very end. So I'm going to take the number that my calculator gives me with the extra sig figs, multiply that by 2, and I get 8.775 and change. And now I round off to get 8.8. Okay. Now some of you are saying, well, Mr. Hendricks, if you take 4.4 and you double it, you get 8.8. Why did I insist on saying that you should take the number on your calculator and double that? Well, because in this time, it worked out okay. We got the same answer this time. But there will be times where if you round off too soon, then you're going to get a slightly different answer at the end than somebody who didn't round off. So whenever you're doing problems like this, where you get some intermediate answer, and then you need to manipulate that intermediate answer to get the final answer, don't round off the intermediate answer. Keep all the extra sig figs and wait until you get the very, very end to round off. Okay, let's see, how are we doing for time here? Okay, we're doing good. We still got lots of time. Okay, so Max is asking, why is it in the air twice as long as it's going up? Okay, I'm glad you asked that, Max. Right? So one thing that is always going to be true of an object in free fall is that when it's going up, it's slowing down, slowing down, slowing down, okay? So the rate of deceleration when it's going up is going to equal the rate of acceleration when it's going down. I think I got too many L's in there, okay? So if the rate of deceleration going up is equal to the rate of acceleration going down, that means that the two halves are going to be symmetrical. So the time going up is going to equal the time going down. So all you have to do is find time going up and then double it. Okay. Now, if the rate of acceleration downward was not the same as the rate of deceleration upward, okay, then it would be different. But with free fall, they will always be the same. Okay. Let's see. Let's go to a couple more problems. I'm skipping a little bit because I'm a little worried we'll run out of time if I go over everything here. Okay. And my chat box went away. So if any of you have a question, I can't see the chat box right now. So if you have a question, you're gonna have to unmute yourself and ask it. All right. So here's another problem like you're gonna see in the homework tonight. Very much like the problem that we just did, but not exactly the same. Okay. Let's turn on annotation here. Oh, good, the chat box just came back. Kind of funny how that works. Okay, good. So nobody's typed any new stuff into the chat box here. All right. Okay. So here's the ground, here's a building, here's some window in the building, So we stick our arm out, so that's our arm, and we're going to drop a ball. And notice I've underlined the word drop here. That's really important. Whenever you see the word drop, that tells you that the initial velocity equals 0. Okay, so let's suppose that I give you a homework problem tonight where you know that the initial height here is, oh, I don't know, let's say that it's 61 meters above the ground. Okay, and so we want to know how much time is going to take to hit the ground. So let's see. Let's make a list of all the variables. That's what I recommend you do for every single problem. I recommend you always start by making a list of all the variables. And let's always do them in the same order so we don't leave some out. So I've got X initial, X final, V initial, V final, A and T. Just get in the habit of always doing them in the same order. Okay. Now, here's where it gets interesting. Where do we pick our origin to be? We could pick our origin down here at the bottom if we wanted. And so I'm going to do that in red. Or if somebody wanted to be different, they could pick their origin up at the top. Okay. So, and also, how about our plus and minus direction? Okay. So up until now, we've said that, most people like the plus direction to be up. Well, what if you're one of those people that likes to be different and you like your plus direction to be down? Okay. Remember how we said that if you choose your origin differently, then that's okay. You'll still get the same number in the end, as long as you don't make any math mistakes. Okay, so let's do this problem with two different ways. So let's do it first. So the red person says that the origin is down at the bottom. So what is X initial going to be for the red person? And what does X mean? X means how far away from the origin is the object at any given time. So X initial means when we start the clock, so when we let go of the ball, how far away is the ball going to be from the origin? Well, if you were to ask the red person, they would say that the ball is 61 meters away. And since they define that the plus direction is up, it's 61 meters away in the plus direction. So for them, X initial is going to be a positive 61. Now, the blue person is going to disagree with that. The blue person is going to say, no, it's not. The X initial is 0, because for the blue person, when we started the clock going, the ball is at the blue origin. So the distance from the origin to the ball at t equals 0 as measured by the blue person is going to be 0. The red person is going to say, no, it's not. It's positive 61. And I propose that it's not going to matter. They'll both get the same answer in the end. Okay, so X final is where is the ball when we stop the clock, so when it hits the ground. So the red person is going to say X final is 0. The blue person is going to say, no, it's not. It's 61. Now notice the blue person is not going to say it's negative 61 because the blue person defined the plus direction to be down. So anything below the blue origin, the blue person calls that positive. Anything above the blue origin, the blue person calls that negative. Okay, now they both are going to agree that the initial velocity is 0. No problem there. Now, what about V final? This is a really important thing that you guys need to understand. Every year, I always have some students that say, well, V final is 0 because when the ball hits the ground, it's going to stop moving, right? So duh, V final must be 0. That is not the case. All of these equations of motion, they only apply when the ball is in the air. As soon as the ball hits the ground, all bets are off. Okay? Think of it this way. If the ball was falling, and while it was falling, some bird came along and grabbed the ball and flew off with it, would you expect that the equations of motion would apply? No, of course not. So hitting the ground is the same thing as a bird grabbing the ball. So do not make the mistake of thinking that the final velocity is 0. You will get all messed up big time if you do that. So in this case, we don't know what the final velocity is. And neither the red person or the blue person knows what the final velocity is. But maybe if we're lucky, we don't need to know the final velocity. Okay, the problem doesn't ask for it. The problem asks how much time does it take? So yeah, maybe we don't need to know it. Okay, so how about the acceleration? The red person is going to say that the acceleration is negative 9.8. What about the blue person? Hopefully you guys have realized that the blue person is going to say, no, it's not. The acceleration is positive 9.8 because the blue person defined the plus direction to be down. Okay, now let me see if I can fix that 8 there, make that 8 be a little bit nicer, 8. Okay. All right, and then how about the time? Well, we don't know. And in fact, that's what we're looking for. So let's put a box around it. Okay, so now it's time to decide which equation to use. Since we're looking for t, whatever equation we choose had darn well better have a t in it, because otherwise it's not going to help us. And since we don't know v final, whatever equation we choose had better not have a vf in it, because otherwise we're going to have a problem. We're going to have two unknowns and only one equation. Okay, so it's time to decide which equation to use. So let's go back to our Dr. Seuss equations up here. Okay, so we need an equation that has a t in it and does not have a v final. Which one is that? Well, hey, it looks to me like it's the mother of all motion equations. See that? It's got a t in it. It does not have a v final in it. Bingo, that is in fact the one that we want. Okay, so let's go down, go back here. Let's see, sorry. Okay, this was the one, right? We're dropping a ball. That's one we want. Okay, so what we do then is we say x final equals x initial plus v initial t plus 1/2 at squared. V initial is 0. And now for the red person, x initial is also 0. So the red person is going to say x final equals 1/2 at squared. And they're going to say that t then, so let's multiply both sides by 2. Let's divide both sides by a. And then we have to take the square root of everything. Okay. So the red person is going to say that t equals the square root of 2 times x final, which whoops, I'm sorry. Sorry, you guys, I'm making mistakes all over the place today. For the red person, x initial is not 0. For the red person, x final is 0. For the red person, x initial is 61. Okay, so that changes things. Let me erase all this. Okay. So for the red person then, we're going to have to subtract 61 from each side. Let's leave it as x final. We're going to subtract an x final from each side. So we're going to have negative x final equals 1/2 at squared. Okay, so we multiply both sides by 2. Divide both sides by a. Okay, and then we take the square root of all that. So the red person is going to say that t is equal to the square root of 2 times x final times negative x final, which for the red person, x initial, sorry. I'm working a little bit too quickly here. And if you guys get confused because I'm going too quickly and I'm making silly mistakes here, I don't blame you. So 2 times negative x initial. So x initial is 61 for the red person, so 2 times negative 61 divided by the acceleration, which for the red person is negative 9.8. Okay, so when I put that into my calculator, I get the square root of, and the negatives are going to cancel out. So 2 times 61 divided by 9.8. So I get the time is 2.487, which if I round off now for sig figs is 2.5. Okay. Now, what is the blue person going to say to all this? And here's where I really need to have more Blackboard space, because I'd like to keep all this red stuff here, but I just don't have room. Now, the blue person is going to start off with the same equation. I wish I could keep everything here. Okay, everybody, hopefully you've written that down. I'm going to have to erase it. I'm sorry, I just don't have room here. I'm going to have to come up with some way to get me more whiteboard space. Oh, whiteboard, I could have used the whiteboard, duh. Oh, I'm an idiot. I could have just used the whiteboard. Oh, well, too late now. Okay, so the blue person is going to have the same equation. X fine, let me do it in blue here so we don't get ourselves too confused. Okay, so the blue person is going to say, well, I got the same equation, X final equals X initial plus V naught T plus 1/2 AT squared. And the blue person agrees that initial velocity is 0, but the blue person disagrees on your X final. The blue person says that it's the X initial that's 0. The blue person says the X final is this. So the blue person is going to have a slightly different equation. What they're going to do is they're going to have X final on the left side and they're going to have all of this on the right. So they're going to multiply both sides by 2, divide both sides by a, take the square root of both sides. And so what they're going to get is that t is the square root of 2 times x final divided by a. Notice that their equation is slightly different than the equation that the red person had, which unfortunately I had to erase. The red person had an equation that had an x initial in it, not x final. And the red person had a negative sign in their equation. The blue person does not have a negative sign in their equation. Okay, but when we plug in the numbers, x final for the blue person is going to be 61. And the acceleration for the blue person is going to be a positive 9.8, not a negative 9.8. And so when the blue person puts in the numbers, guess what? They get the exact same answer that the red person got. Okay. So now you see why it is that I say that you can pick your origin anywhere you want, and you can pick your plus direction to be up or down. It doesn't matter. As long as you're consistent, then you will get the same answer. Okay, now one last thing that we have to do here, and this is going to mess up some people. If you're not familiar with quadratic equations, you're going to have a little bit of a problem here. But those of you that are familiar with quadratics and how to work with them, I think you're going to find this is not that bad. The physics is the same. It's just that the mathematics is a little bit more complicated, or should I say more interesting. Okay. Let's say that here's our building and here's our window, but this time, instead of dropping the ball, this time we're throwing the ball. What does that mean? It means that our initial velocity is not 0 anymore. So let's say that we give it some initial velocity of, oh, I don't know, let's say that it's 18 meters per second upward. Okay. Now, hopefully you guys agree that I can define my origin at the top, I can define it at the bottom, it doesn't matter. So I'm going to just pick an origin, and I'm going to pick my origin to be at the place where the ball was when we started. So by definition then, x initial equals 0. Okay. All right, so x final is going to be below me. So I need to know how high the building was. Anybody remember what I used for my last one there? I think it was 61. So let's keep it the same way here. Let's say that we're dropping it from a height of 61. So it's going to go up here, and so when it hits the ground, it's going to be below the origin. So my x final is going to be a negative 61. My v initial is going to be a positive 18 because I'm going to define my plus direction to be up. Okay, otherwise I wouldn't get a negative 61. My v final is something that I don't know, and maybe if I'm lucky, I don't need to know. My acceleration is going to be 9.8 downward, which for me is going to be negative because I defined the plus up. When you do the homework, if you want to define the plus to be down, that's okay, but that's going to change your x final. It'll make your x final be positive 61 instead of negative 61, but it'll all work out in the end. Okay, and then last one here is time. Well, that's what we're looking for. So let's put a box around it. All right, so I need an equation that's got a t in it and does not have a VF in it. Well, guess what? It's the same equation we just got through using. That's nice, right? So let's write that equation. So x final equals x initial plus v initial t plus 1/2 at squared. Now, the last problem that we did, v initial was 0. That made life easy. It's not 0 anymore. Okay, so we are not going to be able to solve this just by, using what I like to call the 9th grade math technique. We're going to have to use a 10th grade math technique. We're going to have a quadratic equation. So let's just go ahead and plug in the numbers. So x final here is going to be negative 61 equals x initial, which is 0, plus v initial, which is 18, times t, plus 1/2 times negative 9.8 times t squared. Okay, all right, kind of running out of space there. All right, so those of you who are familiar with quadratics, you're going to look at this and say, okay, no problem, that's just a quadratic equation. I know how to do that. So let's add a 61 to each side, because remember, in order to use the quadratic formula, which is the way I recommend you do this, it has to all equal 0. So I'm going to plus 61 to each side. So I get 0 equals 61 plus 81t minus, so 1/2 times 9.8 is 4.9. So negative 4.9 t squared. All right. So now all I have to do is apply the quadratic equation. Remember that one? Remember x equals, let's all sing the song together. So even though, actually, can everybody unmute yourselves? And let's all together sing the song. So everybody push down the space bar, everybody unmute yourselves, and all together we're going to sing the quadratic equation song. So 1, 2, 3, go. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Oh, that was beautiful, guys. Oh, I'm glad this is being recorded. That was wonderful. Okay, so all we have to do then is just plug that into the quadratic formula. Now, do you guys have the quadratic formula programmed into your calculators? Here, you definitely need to have that programmed into your calculator. Let's see. So let me go to, okay. If you go to the Canvas page for physics, you see this button right here that says class resources. This is something that we really haven't done anything with before. Okay, if we scroll down to a video right here, it says to learn how to program the quadratic formula into your calculator, click here. Okay, so let's click there. What you're going to see is it's going to take you to a page here where I've got some YouTube videos where it tells you how to program the quadratic formula into your calculator. Okay, so if you have a TI-83 or 84, use this video up here on the top. If you have an Nspire, use this video on the bottom. Okay, so all you have to do is take the equation that we just came up with, put it into your quadratic formula, and solve it, and it'll tell you what t is. Okay. All right. Now we're running out of time, so I unfortunately, due to time limitations, I don't have the time to finish the problem up here because we're running out here. But if you just type it into your equation there, you'll be good. Remember, the quadratic formula says ax squared plus bx plus c equals 0. except for us, it's going to look a little differently. It's going to say a times t squared plus b times t plus c equals 0. Okay, so for us, a is going to be negative 4.9. B is going to be whatever our initial velocity was, which I don't remember what it was, but you can look it up. And then C, you get that from the previous page there. And then plug that in. And then now your calculator is going to give you two numbers. One of your numbers is going to be a positive number, and the other number is going to be a negative number. Well, time can't be negative, so you can rule that one out. Whichever one of those numbers is the positive number, that's the answer. Okay, so I realize that I did that a lot faster than I would have preferred. And I apologize, but there's just not enough time, especially when we start 10 minutes late. There's just not enough time. So I have maybe time for one quick question. Now, I'm sure you're wondering what the homework is. Actually, I need to stop right now. We are now officially out of time. Okay, so let me just quickly go here to, let's go to the homework. Now, you guys know, of course, you can just look on Canvas and it'll tell you on Canvas what the homework is. Okay, so here it is. Here's the homework, problems 34, 39, and then do 42 through 52 and do all of those. Don't forget my 1 hour policy. If you work on something for an hour and you're not done, you can turn it in and just invoke the 1 hour policy and I'll give you 9 out of 10. Okay, with that, let me just ask again, are there any questions? Not seeing any, not hearing any. Okay, can everybody in the B-Day class, please type bye into the chat box, and I will see you guys on Thursday. Those of you in the A-Day class, I'll see you guys, well, actually in B-Day class, I'll see you on Wednesday. Those of you in the A-Day class, those are the ones I'll see on Thursday. Okay, I apologize for going so fast. I really do. I feel bad about that. Bye, everybody.